Yeah, today we will come to this lecture 6 of module 2. We will be discussing about the plasticity equations, because when you wanted to go further, we wanted this certain terminology which somehow was not discussed earlier. So, if you look at we have already discussed the case that the flow rule, when the stresses at a given point in a material reaches a certain level, the plastic deformation or flow of the material starts. Okay. So, that is the condition of yield criteria as per Tresca or Owen-Messier criteria. So, that means we have that the stresses reaching a certain value, then as per Tresca criteria, maximum shear stress is found, and then for Owen-Messier criteria also we have discussed about the equations under what condition the plastic deformation will take place. Okay. So, many times for analysis purpose, so it is required to arrive at certain relationships between the applied stress and the velocity field. Velocity field, either velocity or the strain field or the strain rate fields. So, this relationship between the stress and the strain, or stress and the strain rate, or stress and the velocity, this relationship we wanted for analysis purpose. So, the relationship between relations between applied stress and velocity or strain rate fields are required for analysis. So, in the direction of the principal axis, in the direction of the principal axis, these relations exist in the following forms. That is, if you just look at it, epsilon dot 1 is equal to lambda into sigma 1 minus your mean stress or hydrostatic stress, if I just put it as 1.1, and epsilon dot 2, the strain rate along this direction, lambda into sigma 2 minus sigma m, that is your mean stress, and epsilon dot 3 is equal to lambda into sigma 3 minus sigma m. This is 1.3. Okay. And these equations are called as the plasticity equations. The variable lambda, this lambda depends upon direction of plastic flow, the temperature at which you are deforming, the strain and the strain rate. So, this is the thing, this depends upon these parameters actually. And we can write this equation, this flow equation in a different way. So, taking into consider the strain increments also we can write. For example, say equation 1.1 we can write in this form as d epsilon 1 is equal to 3 by 2 into epsilon bar by sigma bar. In that format also we can write, where this epsilon bar and sigma bar, they are called as the, see, sigma bar is the effective stress or equivalent stress, or this is called as the effective strain. And from this we can write epsilon dot 1 is equal to 3 by 2 into epsilon dot effective strain rate by this one. We can arrive at this relationship also, sigma 1 minus sigma m. Oh, here I did not write this, sigma 1 minus sigma m, where sigma m is the mean stress or hydrostatic stress. So, we can write it in this form. Now, why? Because this we have to discuss in the subsequent part today itself. So, let us come to this power and energy for deformation. This part we have not discussed, because during the plastic working we have to always know what is the power for the deformation and what is the energy for the deformation. So, this is very much important from a practical point of view. The power is very important actually. So, in this if you consider a homogeneous deformation of a rectangular block, so maybe the rectangular block was like this with these dimensions and other things and axis. So, let us just a rectangular block is being deformed. So, where this is your length L and this is your width and maybe this is your height and you are applying stresses, maybe a generalized say sigma 1 here, these are your principal stresses, sigma 3 here in this direction and maybe in this direction sigma 2. Okay. So, if you just complete this, okay, even in this direction also it is there. So, so, a rectangular block of size L by W by H is there and it is compressed along the H direction. So, if we can say that the strain epsilon H at any instant, say, we can say as epsilon 1 is equal to log H by H naught, and maybe if you consider the strain rate along this direction is equal to your V H by H. Instantaneous value of the velocity by the instantaneous height. So, that is what your strain rate is there. We have discussed earlier. Similarly, we can write epsilon 2 is equal to log 2 is equal to W. Okay. So, W by W naught, and this strain rate along this direction 2 is equal to your V into V of W by W, and epsilon 3 is equal to log L by L naught, or epsilon dot 3 is equal to your V L along the direction L by L. So, these three equations are there. So, from this under these stresses, the material has deformed by a small amount, a small amount. So, we can just write by a small strain increment in all the direction if it is there. So, how what is the power? So, the power you know that is the force into velocity. So, power P is equal to force into velocity. So, that is P is equal to, if you look at all these directions, sigma 1 into this is W, this is L, okay, and this is H. Okay. So, P 1 into W into L into V H plus sigma 2 into H into L into V W plus sigma 3 into H into W, H into W into V L. So, from the above relationship, from A, we can write it as P is equal to sigma 1 W L H epsilon dot 1, because V H is equal to H into epsilon dot 1 plus sigma 2 into H into L into W into epsilon dot 2 plus sigma 3 into H into W into L into epsilon dot 3, or that we can write it as W into L into H is equal to the volume V. So, that we can write it as it is equal to V into sigma 1 epsilon dot 1 plus sigma 2 epsilon dot 2 plus sigma 3 epsilon dot 3. So, this is the power which we can get it if you know the strain rate and the velocity. Okay. So, and the stresses, okay, the principal stresses if you know. Now, if you look at the energy of deformation, E, that is equal to, you have to just integrate it. Okay. So, that is equal to V into integral sigma 1 epsilon dot 1 plus sigma 2 epsilon dot 2 plus sigma 3 epsilon dot 3, the whole into integrating with respect to time. Okay. Because since epsilon dot dt is equal to d epsilon. So, we can write this as V into volume into integral from 0 to epsilon 1 sigma 1 d epsilon 1 plus integral from 0 to epsilon 2 sigma 2 into d epsilon 2, the strain increments we are writing, plus integral from 0 to epsilon 3 into sigma 3 d epsilon 3. Okay. So, this way we can write out the total energy of deformation. Okay. See, many times it is necessary to relate the uniaxial flow stress sigma 0 to the multiaxial material flow behavior, and considering the element and the principal directions, the deformation energy dW expended during the time interval dt. So, relation between uniaxial flow stress sigma 0 to the multiaxial flow behavior And considering the element and the principal direction, the deformation energy delta W, the deformation energy during a small interval time, the deformation energy expended during the time interval dt delta t is dW is equal to sigma 1 d epsilon 1 plus sigma 2 d epsilon 2 plus sigma 3 d epsilon 3. So, we can write that dW by V also per unit volume. Okay. So, this is that is per unit energy per unit volume. Okay. So, the deformation power P is equal to dW by dt. So, that will come to sigma 1 d epsilon dot 1 plus sigma 2 d epsilon dot 2 plus sigma 3 into d epsilon dot epsilon 3 into. So, this if you write it in terms of effective strain rate, strain and strain rate, we can define the effective strain and the strain rate. In terms of effective strain epsilon bar and strain rate. Epsilon bar dot, we can define it as dW is equal to sigma bar into d epsilon bar into V. So, let us write it as equation number 3. And so, we can write P is equal to, so, sigma bar into epsilon bar dot into V. So, this leads to epsilon dot bar is equal to sigma 1 epsilon dot 1 plus sigma 2 epsilon dot 2 plus sigma 3 epsilon dot 3. If you apply the constant volume relationship, constant volume relation is, see, strain, sum of the strains are 0 and similarly it is the sum of the strain rates are also 0. So, that or sigma m, the hydrostatic stress into epsilon dot 1 plus epsilon dot 2 plus epsilon dot 3 is equal to 0, we are getting 5. So, from this 4 and 5, we can get this relationship sigma bar epsilon dot bar is equal to epsilon dot 1 into, from the plasticity relationship. Okay. So, that is as what we discussed in the morning itself, sigma 1 minus sigma 2 plus epsilon dot 2 into sigma 2 minus sigma m plus epsilon dot 3 into sigma 3 minus sigma m. So, earlier we have discussed this relationship. So, that will lead to say, cubed root of square root of 2 by 3 sigma naught is equal to sigma 1 minus sigma 2. See, this is the one Mises criteria, plus sigma 2 minus sigma 3 square plus sigma 3 minus sigma 1 square, the whole raised to 1 by 2. This is the one Mises criteria. So, from this relationship we can write it as epsilon dot bar is equal to epsilon dot 1 into sigma 1 minus sigma m plus epsilon dot 2 into sigma 2 minus sigma m, where sigma m is the hydrostatic stress, plus sigma 3 minus plus epsilon dot 3 into sigma 3 minus sigma m divided by 3 by 2 into sigma 1 minus sigma 2 square plus sigma 2 minus sigma 3 square plus sigma 3 minus sigma 1 square, the whole raised to 1 by 2. So, this is equation number 6. And we also arrived at that sigma dot 1 is equal to lambda into sigma 1 minus sigma m, and epsilon dot 2 is equal to lambda into sigma 2 minus sigma m, the first slide itself. No, sorry, I think it was first slide, no? Yeah, right. And epsilon dot 3 is equal to lambda into sigma 3 minus sigma m. So, using the plasticity equation, we can write it as sigma 1 minus sigma m is equal to lambda dot 1 epsilon dot 1 by lambda, and sigma 2 minus sigma m is equal to epsilon dot 2 by lambda, and sigma 3 minus sigma m is equal to epsilon dot 3 by lambda. So, using these equations, applying this, in equation number 6, we get the effective strain rate. So, effective strain rate epsilon bar dot is equal to, if you substitute, you will get as 2 by 3 into epsilon dot 1 square plus epsilon dot 2 square plus epsilon dot 3 square. And if we integrate it, the effective strain can be obtained from this is equal to integral from T 2 to T 1 dt. See, this is how we can calculate the effective strain and effective strain rate for your plasticity problems. Okay. Now, with this in background, let us do one or two problems. Today we can do that. So, the question number 1 is since we have not discussed about it and assignments are given, but I thought it is always better to do some problem in this relationship. So, the question number 1 is the strain gauges are attached on the surface of aluminum of an aluminum sheet for measuring the stresses. So, there was an aluminum sheet, so its thickness is very less. You can assume that it will be a plane stress condition. Stresses are along a plane only, third direction there is no stresses. Okay? So, that we can assume because it is very thin. And during the test, the following stresses are recorded at a particular instant. Any instant you found this, these were the stresses which were the values which were obtained from the strain gauges in the particular directions. Okay. So, one is you found that sigma xs is equal to 90, okay, sigma yy is equal to 110 megapascal and tau xy is equal to 50 megapascal. So, these three things we got it. If the uniaxial yield stress of the material sigma 0 is equal to 150 megapascal, determine the yielding for both the Tresca and von Mises criteria by assuming biaxial stress conditions. So, if the uniaxial yield strength of the material sigma 0 is 150 megapascal, determine the yielding for both the Tresca as well as for von Mises criteria, assuming this one, assuming that it is a biaxial stress condition, because when it is thin aluminum sheet we can always consider it as a biaxial stress condition. Okay. So, not triaxial, because along the third axis the stresses can be neglected, that is what the basic assumption we are going to take it. Now, this problem can be done by two methods. One is by a simple method is by the drawing the von Mises drawing the Mohr circle and finding out determining the values, and another is by the mathematical analytical method using the stress invariance which we have discussed in the earlier classes, the state of stress, there we have discussed about the stress invariance. So, that by using that we can do it. So, it is like first let us discuss about how to solve this by von Mises criteria, though you have by Mohr circle determination, though you have studied that in the classes, at least for revision this will be of helpful for you. So, in a biaxial state of stress, if I just draw the circle like this. So, this is your sigma 1 principal stress, this is your sigma 2, and if I draw at a state of stress at any instant, say with this as theta. So, if I just drop this largest one give you sigma xx, and if I drop the projection, this will give you sigma yy, and this will give you your tau xy. Okay. This is the general, and this is your 0. So, this is your tau and this is your sigma. Okay. In this direction you can write it, and here it may not be good, here we will have to write. Okay. So, applying this is theta, applying the Mohr circle from the mathematics part of that, we can write it as sigma 1 is equal to sigma xx plus sigma yy divided by 2, that is your half part here which is coming, plus square root of sigma xx minus sigma yy by 2 the whole square. So, that means this radius square, okay, plus tau xy the square is to 1 by 2. This is the mathematical relationship. If you look at this, we can always find out what is sigma 1, and similarly sigma 2 will be the same thing, only here it is negative. Sigma xx plus sigma yy divided by 2 minus sigma xx minus sigma yy divided by 2 the whole square plus tau xy square the whole raised to 1 by 2. Now, we get that this value is sigma xx is equal to 110 is equal to 1110 megapascal, and this is equal to 60 megapascal. okay, and this value is equal to 50. Okay. So, if you just substitute, so we can find it out, sigma 1 is equal to 110 plus 60 divided by 2 plus 110 minus 60 divided by 2 the whole square plus 50 square the whole square. So, that you will get you will arrive at 140.9 megapascal. Sigma 1 is equal to 140.9 megapascal, and sigma 2 is equal to, since it is negative, so you will find 110 plus 60 by 2 minus 110 minus 60 by 2 the whole square plus 50 square raised to 1 by 2, that you will get it as 29.09 megapascal. And so, you know that sigma 3 is equal to 0 because it is a biaxial state of stress. So, sigma 3 is equal to 0, that we know that. So, now let us look at the, as per the Tresca criteria, the material will start plastically deforming or yielding when the shear stress, the maximum shear stress is the half of the largest and the smallest principal stresses. Okay. So, in this case it is equal to, now let us check as per the von Mises criteria, the yielding can take place under this condition. So, when you look at it as von Mises criteria, it is that your second invariant I2, when it crosses certain level, plastic deformation take place. So, that is given by, say, plastic deformation will take place when it crosses certain value, that is 1 by 6 into your sigma 1 minus sigma 2 square plus sigma 2 minus sigma 3 square plus sigma 3 minus sigma 2 square, sorry, sigma 3 minus sigma 1 square. So, this is the condition. So, if you just find that value, that is equal to 1 by 6 into 112 square, because sigma 1 is equal to 140.9 minus sigma 2 is equal to minus 29.09 square plus 29.09 square. You can take 29 itself plus 140.9 or 141 also we can do it, it is not going to make much of a difference. So, this value comes to something around 5505 megapascal square, we can say. Second invariant comes to this value. So, like this the yielding criteria, that means yielding will occur or plastic deformation will occur, it will take place as per the von Mises criteria when I2 reaches a critical value k, where k square is equal to sigma naught uniaxial yield strength of the material, that is sigma naught by 3. So, since sigma naught is equal to, in our problem, sigma naught is equal to 150 megapascal, this is equal to 150 square by 3, this comes to 7500 MPa square, this is the energy, okay, distortion energy, this is what. So, yielding will take place when the distortion energy reaches the value of 7500 megapascal square, but since in our based on our principal stresses, the value of I 2 is only 5504, since I 2 is equal to 55.05. Since this second invariant is in our case it is 5505, which is much less than this critical value of 7500 megapascal square, you will find that is yielding will not take place, that is deformation will not take, plastic deformation will not take place. Deformation will not take place, will not occur. Now, let us just consider that Tresca criteria. The Tresca criteria states that the tau max, when it reaches a critical value, that is tau max decided by sigma 1 minus sigma 3 by 2, it reaches a critical value which is equal to reaches a critical value of that is equal to sigma 0 uniaxial yield stress by 2. Okay. So, that is equal to, so let us see that this tau max is equal to, our sigma 1 is equal to, what is the value, 141 we can write, and sigma 2 is equal to 29, sigma 3 is equal to 0, that is 141 minus 0 divided by 2, it is 70.5 megapascal. And this critical value is sigma 0 is how much is sigma 0? 150. 150 divided by 2, that is equal to 75. So, when this is, since tau max is equal to 70.5 megapascal, which is less than critical value 75. So, under both the condition, yielding will not take place. So, this is what so in this case what you have to find out, you find out the principal stresses and then you apply the von Mises criteria and the yield criteria. The second method is by finding out the stress invariance. Okay. So, that method also we will just discuss. So, this same problem of finding out the principal stresses by the invariance, tensor invariance, no, we can also do that. See, because what are the things which are given for us is sigma xx is equal to 60 megapascal, sigma y is equal to 110, and tau xy is equal to 50, and sigma 0 is equal to 150 megapascal. These are the things which we have given. So, since it is this one biaxial stress, no, like we can assume that sigma z is equal to 0, tau y z is equal to 0, tau x z is equal to 0. Okay. So, the solution when you do it, earlier we have discussed in that I think in the first or second lecture, the principal stresses sigma p is the principal stresses, we got a cubic equation sigma 3 cubed minus the first invariant I 1 into sigma p square minus I 2 the second invariant into sigma p minus I 3 is equal to 0. Okay. So, if you look at that where I 1, I 2, I 3 are the invariants. Okay. Invariants I 1, I 2 and I 3. So, what are these I 1, I 2, I 3? So, let us say that I 1, the first invariant which we have written earlier itself is equal to sigma x x plus sigma y y plus sigma z z. So, sigma x x plus sigma y y plus sigma z z. Sigma z z is 0. Okay. So, I 2 is equal to tau squared y z plus tau z x plus tau square x y minus sigma y y sigma z z minus sigma z z sigma x x minus sigma x x sigma y y. Okay. And similarly, I 3 is equal to sigma x x sigma y y sigma z z plus 2 into tau y z into tau x z into tau x y minus sigma x x into tau square y z minus sigma y y into tau square x z minus sigma z z into tau squared x y. So, this is, if I write this as equation number 1, this is equation number 2 and this is equal to equation number 3 and this is equation number 4, this 4 equation. Now, we have to solve it. So, let us find out what is the value of I. I 1 is equal to sigma x x plus sigma y y plus sigma z z, sigma z is equal to 0. So, sigma x s is equal to 60 plus 110 plus 0, that is equal to 170, and I 2 is equal to only 2 terms are coming. So, that is your sigma x x sigma y y and tau x y square, all others are 0 because sigma these terms are 0. So, you will get it as 50 square, that is tau x y square minus so, here if I just write like the tau x y square minus sigma x x sigma y y. So, that is equal to 50 square minus 60 into 110, that is equal to minus 4100. So, that is the I 2 you are getting, and I 3 is equal to 0 because it is all the terms are 0, because here multiplication by 0 is coming in all the terms, it is 0. So, I 3 is equal to 0. So, if you substitute this that is I 1 is equal to 170 and I 2 is equal to minus 4100 in equation 1, you will get, that is 6 sigma p cubed minus I 1, that is 170 into sigma p square minus I 2, that is equal to minus 4100 into sigma p is equal to 0. So, that is anyway sigma p is common. So, we can write it as sigma p square minus 170 sigma p, these are the principal stresses, plus 4100 is equal to 0. Binomial equation. So, that is sigma p square minus 170 sigma p, minus 4100 is equal to 0. So, this if you solve it, you can write it as following for sigma p. Sigma p is equal to what is that? So, y is equal to minus b plus or minus square root of b square minus 4 ac by 2a. Okay. So, that if you look at it, it will be minus 170, that is 170 plus or minus root of 170 square minus 4 into minus, this is plus, minus 4100 into 4 AC into 1, okay, by 2 into 1. So, that is equal to 170 plus or minus root of this, this will come to around 12500 divided by 2. So, one of the solution is what is sigma 11 is equal to, you can write it as 170 plus or minus root of 12,500 divided by 2, and sigma 2 is equal to 170 plus 170 minus root of 12,500 by 2. So, this comes to something 140.9 and this is 29.1 megapascal. So, this is how you find out the principal stresses. So, you can do by any of this method, either by from Mohr circle representation or by solving this analytical equation, you can find out. Once you find out this principal stresses, then you can check for whether the yielding will take place as per the Tresca criteria or as per the von Mises criteria which is asked in the question. So, that we have already solved it. Okay. The remaining, so the sigma 1 and sigma 2 we have got it. So, you can solve it by any of this method. Let us now come to the second question. The strain hardening of an annealed metal, a strain hardening, the strain hardening of an is expressed by this relationship sigma bar, that is effective strain or average strain, is equal to 240 into epsilon bar 0.4 megapascal. Okay, there should be a bracket. So, the given is that the sigma bar is equal to 240 into epsilon bar, otherwise people may, the way I have typed it, people may think that it is minus 0.4. And so, we can write it as d 0 is equal to 25 mm, d 1 is equal to 20 mm and d 2 is equal to 10 mm. So, that means a 25 mm diameter bar is drawn down to 20 mm diameter, and after that subsequently to a 10 mm. So, this was the two steps. In the first step it was reduced to 20 mm diameter, and the second step it was reduced to 10 mm, and this was done using a conical die. Determine the plastic work for per unit volume of each. Plastic work per unit volume for each reduction. Okay, that is the question. So, we know that the plastic work du is equal to sigma bar d epsilon bar. Okay. See, this is the thing, and epsilon bar we can write it in this form, that is equal to epsilon 1 minus epsilon 2 square plus epsilon 2 minus epsilon 3 square plus epsilon 3 minus epsilon 1 square, the raised to whole raised to 1 by 2. This is the effective stress. Okay. And epsilon bar is your effective strain also. So, that is what. Maybe because it is cylindrical, in the bar is in a cylindrical piece, the workpiece is a cylindrical piece, and you are also drawing it into a cylindrical piece, output also is a cylindrical piece. There is a symmetry. So, from as per the symmetry of the sample, as the symmetry we can write it as epsilon 2 is equal to epsilon 3. And if you apply the constant volume relationship, that is epsilon 1 plus epsilon 2 plus epsilon 3 is equal to 0. So, that means epsilon 2 is equal to epsilon 3. So, that will come to minus of epsilon 1 by 2. This is how we will get from this relationship we will get it. So, now we can calculate what is the effective strain. So, effective strain will be, so if I just put this as equation number 1, from 1, effective strain is equal to root 2 by 3, sorry, here it is root 2 by 3, root 2 by 3 into epsilon 1 minus epsilon 2. So, that means epsilon 1 minus epsilon 2 is equal to minus epsilon by 2, the whole square, plus minus epsilon 1 by 2 the whole square, minus of epsilon this one the whole square, plus epsilon 3 that is equal to minus epsilon 1 by 2 minus epsilon 1 the whole square raised to 1 by 2. So, that is equal to root 2 by 3 into this is 3 by 2 epsilon 1 square plus 0 and plus again this is 3 by 2 epsilon 1. Okay. So, that is minus of. So, minus 3 by 2 epsilon 1 the whole square raised to 1 by 2. So, that you will get it as is equal to epsilon 1, that is effective strain epsilon is equal to epsilon 1, not I, epsilon 1. Okay. So, that is what we are getting. Now, we can find out. See the question number, if I say the first step A, first reduction, that is from 25 to 20 mm dia. So, your epsilon 1, because it is stretched, it is just wire drawing only. Epsilon 1 you can write it as is equal to log A naught by A. What was the initial cross section area and the instantaneous value. Instantaneous value is initial was 25. So, this can be in terms of diameter, you can write it as A is equal to pi by 4 d square. So, that means numerator and denominator pi by 4 will go off. So, we can say that d 0 by square by d 1 square. So, that is equal to 2 log d 0 by d 1. So, that is equal to, you will get 2 log 25 by 20, and that you will get it as 0.446, that is what you are getting. So, the plastic work U1, so this is your first case, epsilon 1 is equal to 0.446. The plastic work per unit volume is equal to d U1 is equal to integral du So, that is equal to integral from 0 to 0.446 sigma bar d epsilon bar. So, what is directly you can write as 0.446 integral within this limit 240 into epsilon bar raised to 0.4 d epsilon bar. So, that if you do it here, so u1, that is u1 is equal to integral 240 into epsilon bar raised to 0.4. This is from integral from 0 to 0.446 is equal to 240 into epsilon bar raised to 1.4 divided by 1.4 between this 0.446, okay, or that we can say 240 by 1.4 into 0.446 raised to 1.4 minus 0 raised to 1.4. So, this comes to around 55.35. Okay, this is equal to, so u1 is equal to 55.35, unit will be Newton millimeter per millimeter cubed. This is the first one. Now, B, the second reduction. That is from 20 to 10 mm. Diameter. So, there if you find out the strain, so that means epsilon 2 is equal to 2 log 20 by 10, that is equal to 2 log 2 is equal to 1.386. So, the first reduction, the strain was 0.446, and with that, because if it is a annealed material, you have to calculate from, because you should know about the strain history. So, in the strain history, after the first step, already it has been strained to 0.446. Now, from 0.446, another strain is coming, which is around 1.386, the total strain. So, total strain will be epsilon 1 plus epsilon 2, that is equal to 1.386 plus 0.446. So, that comes to 1.832 total strain. So, final strain you will find it is 1.832. You should not make this as 1.386. So, in now this U2 plastic energy work. So, we can say du2 is nothing but integral from, you have to start with the previous one, that is 0.446, integral from 0.446 to 1.832. This is the final strain. So, which will come to say 240 into epsilon bar raised to 0.4. This is your flow stress equation. So, that it will come to 240 divided by 1.4 into epsilon bar raised to 0.4 between the limits 0.446 to 1.832 d epsilon. Oh, here d epsilon is required. I somehow forgot it. No, here d epsilon is required. Here d epsilon. Let me just see whether d epsilon, d epsilon bar. So, this we can get it as 240 by 1.4 into 1.832 to the power 0.4 minus 0.446 to the power 0.4. So, that will come to 344 Newton per millimeter cubed. So, if you just look at the value of the plastic work which has been done from 25 to 20, it is only very small amount compared to say 20 to 10 mm diameter. There is a big difference. So, it is almost coming to say around 6 times or something approximately. So, these are the two cases we are finding out.